Okay, so welcome back. All right, so this week we're going to continue on with graph algorithms. Right, so last week we talked about some graph traversal problems like BFS and DFS. We also looked at weighted and directed graphs. Right? We introduced those. So now this week we're going to look at some algorithms on directed graphs and weighted graphs. All right, so first of all, let's talk about directed graphs. All right, so let's remind ourselves what a directed graph is. Right, so a directed graph is a graph where each edge has a source and a destination. All right, and unlike undirected graphs, even though there is an edge from V to W, it doesn't necessarily mean that there is an edge from W to V. Right, so edges are directed, and you might have edges going in both directions, but you might not. Right, and here are some applications of directed graphs, just repeated from last time. So the internet is a giant directed graph, right? And in this representation, the vertices would represent your web pages, and your edges would represent hyperlinks. Okay. Another example is chess. So in this application, your vertices would represent your board states, right? So that in a chess game, there are a finite number of board states. There are lots, but there is a finite number. And there would be an edge between two board states if there is a legal move that takes you from one board state to the other. Right, and here are some other examples. So scheduling a program. So in a program, your vertices would be your function calls. Your vertices would be your functions, and edges would represent function calls. Right, and your make is also another example. So your vertices would represent your targets, and your edges would represent dependencies, right, between your targets. All right, so let's talk about traversing a directed graph first. Right, so it turns out that traversing a directed graph is pretty much the same as for undirected graphs. Right, so the algorithm we use is exactly the same. Right, so look at BFS. Right, so BFS just uses a visitor array, uses a queue, and we just have a loop where we remove a vertex from the queue, and then we check our neighbors, right? And then for any that haven't been visited, we mark them as visited, and we in-queue them. Okay, so now DFS. So DFS is also implemented in the same way, right? So we create a visitor array, then we have a recursive helper function that takes in the visitor array and the current vertex, and that function just recurses, right? So the function marks the current vertex as visited, and then for each neighbor of V, we recurse into that vertex. All right, so digraph traversal, the same in directed graphs as in undirected graphs. Right? And of course, you could also implement DFS iteratively using a stack as well. All right, so here's an application of digraph traversal. Right? So we said earlier that the internet is a giant directed graph, right? Where the vertices represent web pages and your edges represent hyperlinks. Right? So, and it's directed because even if one page has a hyperlink to another page, that doesn't mean that page has a hyperlink back. Right? So it's a directed graph. Right? So one application of digraph traversal is to web crawl, right? And what is web crawling? It's, you start at a particular page on the web, and then you want to visit visit pages that are accessible via that page, right? So you start at some websites, then you follow the links to other websites, and then you follow the links on those websites to go to other websites, and so on. Right? So the goal is to visit a subset of the web, right? And why might we want to do this? Well, we might want to index these web pages. So what I mean by index is, to grab, keywords from each page and then store them so that you can implement something like a search engine, right? So search engines, they need to crawl the web, right? So, Google, Bing, Yahoo, and so on, right? And also, you might want to crawl web pages so that you can cache the web pages locally, right? So Google caches web pages, right? All right, so which traversal method would we want to use, if we wanted to crawl the web? Well, we have, BFS, we have DFS. So which one is more appropriate, right? So let's think about this. Remember the difference between BFS and DFS, right? BFS visits vertices, that are closer to the vertex first, right? They visit vertices in order of distance from the starting vertex, right? So that's BFS. What does DFS do? Well, DFS tries to follow, a path as far as it can go, right? So it, follows the path as far as it can go, and once it reaches a dead end, it backtracks and then finds another path to follow, right? So out of those, if you use a DFS, right, let's say we start at a UNSW website and we run a DFS, right? If we do that, since DFS follows a path, tries to go as far as possible down a path, it's possible that, it's very likely, in fact, that we're going to end up visiting pages that are very unrelated to UNSW very quickly, right? Because we're just following links. Let's say we just follow a random link on each page. We're going to get out of UNSW domain really quickly and find something irrelevant, right? Whereas BFS, since we're visiting all the pages that are closer to our starting website first, we're much more likely to get websites that are related to UNSW, right? So BFS is more likely what we want to use, right? Because we want to visit pages that are closely related to the pages that we started at. All right, and one thing about web crawling is that we can't really use a visitor array, right? Because with a visitor array, we have an array of v booleans where each boolean keeps track of whether we visited the page, right? With web crawling, we can't do that because we don't know how many web pages there are, right? So what we do instead is we use a visited set, right? That just contains all the web pages that we visited so far. Okay. All right, so here's what this crawling algorithm might look like. All right, so we take in a starting URL and the number of pages that we want to visit at most, right, max pages to visit. Then we create our visited set. Right, we add our starting URL to the visited set, and then we enqueue our starting URL. Right, so we're still using a queue, just like with normal BFS. Then we enter our main loop, right, and our main loop here also has this condition that we don't exceed the maximum number of pages that we want to visit. Right. And then inside the loop, we remove a web page or a hyperlink from the queue. We visit the web page, right? And then we check all the hyperlinks on that page. And for each of those hyperlinks, if we haven't visited that page yet, then we add it to the visited set and we enqueue it. Okay, so yeah, that's one way we would crawl the web. Right, so I guess a more fun application of digraph traversal or web crawling is a wiki game, right? So what is the wiki game? Well, if you're given 2 Wikipedia articles, you want to navigate from the first article to the second in as few clicks as possible, right? That's the game. So one way you could, find the shortest path from, one Wikipedia page to another is to crawl starting from, one of the articles, right? And then you find the shortest path from the first article to the second, because you're using a BFS. All right, so that's just one application of digraph traversal. All right, so let's talk about a different algorithm. So let's try and find cycles. Right, so we solved the cycle problem for undirected graphs in week 5. So let's see if we can do this for directed graphs. All right, so for directed graphs, what is a cycle? So a cycle is a path, right? It's a directed path where the start vertex is the same as the end vertex. Right, so in this graph, so here is a directed graph. Right, what are the cycles? Well, we have 3 cycles, so 0, 4, 0. Right, so this now counts as a cycle, unlike in our undirected graph. We also have 2, 5, 6, 2. And we also have the self-loop 3, 3. Right? So in directed graphs, self-loops count as cycles, and so do 2 vertices that have edges to each other. Okay, so let's remind ourselves how the cycle checking algorithm for undirected graphs works. Right, so how did this work? We created a visited array, right? And then we basically performed a DFS, right? Where during the DFS, if we see a vertex that we've already visited before, then that means there's a cycle, right? Except for undirected graphs, we had to make sure that we ignore the vertex that we just came from, right? Because otherwise, it would treat going back and forth along a single vertex, so along a single edge, as a cycle. Right? So that's why we have this previous argument here. All right, so the question is, does this work for directed graphs? Well, the answer to that is unfortunately not. Right? So it doesn't work for directed graphs. And there are a couple of reasons why it doesn't work. So the first reason is that the algorithm ignores the edge to the previous vertex, remember? And therefore, it's not going to detect this kind of cycle. Right, so I can show that over here. So here I have the cycle checking algorithm that we implemented in week 5. Right, so it's exactly the same. I haven't changed anything. And I have some test cases. Right, and the very first test case is just a graph where we have 2 vertices that have edges to each other. Right, so 0, 1, and 1, 0. Okay, so if I now run the program on this graph, right, it's going to say that there is no cycle, right? But it should say that there is a cycle. And also, I have another test case where we just have a single vertex that has an edge to itself, so it's a self loop. So if I run the program on this, it'll also say that there is no cycle, right? But it should say that there is a cycle. All right, so how do we fix that? Well, it's simple. So we just don't ignore the edge to the previous vertex. All right, so that means in our recursive helper function, we no longer keep track of the previous vertex, right? And in our loop that goes through all the neighbors, if the neighbor has been visited, then we return true. All right, so let's just modify our algorithm so that to apply that fix. All right, so our function no longer takes in the previous vertex, so I removed that. And that means we only pass in v. All right, and we can remove this if statement, which causes us to ignore the previous vertex. Okay, so let's just delete all of that. Okay, and in our recursive call, we no longer pass in v, right, as our previous vertex. All right, so that's it. Right, now let's see if it detects a cycle in our first two graphs. Whoops, I need to redirect it. All right, so it says that the graph contains a cycle for our two vertices that have edges to each other. And for the other test case, it also says that there is a cycle. Okay, so our algorithm now works for these two test cases. Right, so the question is, does this algorithm now work? Right, and the answer is still no. And why does it not work? That's because there are some graphs where the algorithm can there are some graphs where the algorithm can detect cycles when there isn't actually one. Right, so the example for that is this graph. So a very simple example where we have three vertices, 0, 1, and 2. 0 has an edge to 1, 1 has an edge to 2, and 0 has an edge to 2. Right, so why will this algorithm detect a cycle in this graph? Well, what would happen if we started at 0? Right? So if we start at 0, then it's going to recurse into 1, right? Then it's going to recurse into 2, so it's going to mark both 1 and 2 as visited. Right? Then it's going to reach a dead end, right? So 2 is a dead end, so it's going to backtrack to 1, backtrack to 0, and then it's going to see that 2 has been visited, right? So it'll think that there's a cycle. Right? And if I run the program on this test, which I put in the third file here, so 3 vertices, 0, 1, 1, 2, 0, 2. Right, if I run the program now on this graph, it'll say that there is a cycle. Right, but there is no cycle. So, right, so what is wrong with our algorithm? Right, and how can we fix it? So first of all, let's have a look at what would happen if the graph was undirected. Right, so if we just had this graph with edges between 0, 1, and 2. Right, so here's just a visualization of how the algorithm would work. Right, how our undirected algorithm would work. So we're starting at 0. Right, so our function is going to take in 0, but it's also going to take in the previous vertex. Right, so this is the cycle checking algorithm for undirected graphs. Right, and we mark 0 as visited. Right. Now, what happens? Well, 1 is a neighbor of 0, so we're going to recurse into 1. Right, and we're going to pass in the previous vertex, which is 0. Right, and we're going to mark 1 as visited. Right, now, 1 is going to see that 2 is a neighbor, so we're going to recurse into 2 and pass in 1 as the previous vertex. Right, and we're going to mark 2 as visited. Right. Now, when we're at 2, we see that 0 is a neighbor, right, and 0 has already been visited. Right, so that means that there is a cycle. Right. But also, what we notice is that the reason there is a cycle is because 0 is still on the call stack. Right. So this is the sequence of functions that are being called. Right. What we can see is that we've started at 0 and we've recursed around the cycle, right, so to speak. So we've started at 0, then we've gone to 1, then we've gone to 2, and now 2 has an edge back to 0. So our call stack actually contains this cycle, right? So what we want to do is we want to modify our algorithm so that it checks if the neighbor is already on the call stack. Right, so when the graph is undirected, right, we could do this by checking the visited array. right? So, all we had to do here was to check whether 0 has been visited, and because it's been visited, we know that there is a cycle, right? But for directed graphs, we can't do this because we have directed edges. So it's possible that we recurse over to another vertex and then backtrack, and then later on we see the vertex again, right, via another edge. Right, so what we need to do is we need to use a separate array to keep track of when a vertex is on the core stack. Right? So similar to a visited array, but it just keeps track of which vertices are on the core stack. All right, so here is what this algorithm would look like. All right, so our main function has cycle. We create the visited array. We also create the on-stack array. Right, so we have two arrays here. So visited is the same as in the original cycle checking algorithm. The on-stack array keeps track of whether a vertex is on the stack. All right? And this part is exactly the same as in the original algorithm, except we pass in the on-stack array. All right, now, what does this recursive function do? Right, so the first thing it does is, since V is now on the core stack, right, we mark it as on the stack by setting on stack index V to true. Right, otherwise, well, not otherwise, but at the end of the function, when we return, we set it back to false. Right, so we're using this array to keep track of what's on the stack. Okay, so in this situation, 0, 1, and 2 are all on the stack. All right, now when we check for neighbors in this function, so for each neighbor W, right, if W is on the stack, right, then we return true, right? And that's how we check if there's a cycle, right? For undirected graphs, we just checked if W has been visited. In this algorithm, we check if W is on the stack. So if W is on the stack, we return true. Otherwise, if W has not been visited yet, right, then we recurse and see if there is a cycle from that vertex. Okay, so that is how cycle checking works for undirected graphs. Right, so here's an example of a graph that I also have in my tests. So this should be cycle 4. Right, so this input here corresponds to this graph. Right, so what do we expect to happen when we run our algorithm on this graph? Right? Suppose we start at 0. Right, so if we start at 0, then we're going to recurse into 1. Right, now 1 is a dead end, right? So we're going to return back to 0, and then we're going to recurse into 2. Right, now, when we recurse into 2, and we check 2's neighbors, right, 1 is a neighbor of 2, right, but 1 isn't on the stack, right, because we just returned from 1 already. So 1's not on the stack, so that means we're not going to incorrectly say that there is a cycle. Right, so yeah, so we don't conclude that there is a cycle, and then we move on to the next neighbor, which is 3. Right, so we recurse into 3. Right, from 3, we see that 1 is a neighbor, right, but 1 isn't on the stack. Right, so we don't conclude that there is a cycle. Then we recurse into 4, right? Then we recurse into 5, and from 5 we see that 2 is a neighbor, and 2 is still on the stack, right? Since our stack is currently 0, 2, 3, 4, and 5, right? So 2 is still on the stack, so since it's still on the stack, we return true, right? And because we found the cycle. All right, and let's just demo this by adding some print statements to this cycle function. All right, so oh yeah, we also have to implement the algorithm first. So let's remember how the algorithm works. So our helper function now takes in an array called onStack, right? And at the start of the function, we mark v as being on the stack, right? So onStack v equals true. And at the end of the function, we set onStack v back to false, okay? So keeping track of what's on the stack. Now, the way we check if a vertex has been visited, the way we check if there's a cycle is we check if the neighbor is on the stack, right? If neighbor is on the stack, then we return true. Otherwise, right, if we haven't visited W, then we recurse. Right, let me take these. Okay, so if W hasn't been visited, then we recurse on W, and we pass it the visited and on stack array. And if there's a cycle from W, then we return true. Okay, and there are a few things I have to modify here. So in our hasCycle function, we need to create our onStack array. Right, so we calc it because all the vertices are initially not on the stack, so we initialize to false. And we pass in onStack to our hasCycle function. Right, and we also have to fix this prototype. Okay, so that should be it. Let's see if it compiles. Okay. Right, so first let's make sure that it still works on our initial test cases. Whoops, have to redirect it. All right, so our first graph with two vertices with edges to each other has a cycle. This graph where it's just a vertex with a self loop has a cycle. This third graph, now it says that there is no cycle, which is good. Right, so this was the triangle graph from here. Right, so there isn't a cycle here, and our algorithm correctly says that there isn't. And now cycle 4 is this graph over here, right? So let's see if it detects a cycle, and it does. All right, so we can examine what the algorithm is doing more closely by adding print statements. So let's add some print statements here to see what's going on. All right, so at the beginning of this function, let's say recursed into V. All right, so we recurse into V, and at the end of the function, let's say backtracking from V. All right, so now we know when the function is being called and when it's returning. All right, what else do we want to add? Well, let's add a print statement here when we detect a cycle. All right, so let's say W is on the stack, cycle found. Okay, and let's see, what else do we want to do? Well, I can add a print statement here saying recursing into W, but I already have a print statement here at the beginning of the function, so I don't think I need this. So I think that's it. So let's see what our program prints when we run it on this graph. All right, so what happens? Well, we are starting at 0, right? And we recurse into 0, well, that's the initial function, so it's not really, a recursive call, but later on, we recurse into 1, right? So we recurse into 1. Then, since 1 is a dead end, we backtrack from 1, right? So we backtrack back to 0. Then we recurse into 2, we recurse into 3, we recurse into 4, we recurse into 5, and then 2 is on the stack, right? So we found a cycle, all right? So that's how that function works. Okay, so that's cycle checking. All right, so one more algorithm on directed graphs that I want to look at is related to transitive closure or reachability. Right, so one common problem that you might get is to know whether one vertex is reachable from another vertex. Right, and if your graph is undirected, right, so your edges always go both ways, then it's easy to compute reachability, right? Because all you have to do is to compute connected components, right? And we know that for an undirected graph, if 2 vertices are in the same connected component, then that means it's possible to reach the vertices from each other, right? So there's a path between them. If 2 vertices are not in the same connected component, then there is no path between them, right? But for a directed graph, the problem of reachability is a bit more complicated, right? Because you have directed edges. So even though there is a path from A to B, it doesn't necessarily mean there's a path from B to A. All right, so how might we check reachability in a directed graph? All right, well, one way is to use a BFS or DFS starting at S, right? So I want to find if there's a path from S to T. All right, so this is going to be O of V plus E in the worst case. Right? We analyzed BFS and DFS in week 5, and we saw it was O of V plus E. Right? And the question is, what if this operation is very frequent? Right? What if we often need to answer questions such as, can I reach T from S? Right? So if we just use a BFS or DFS starting over from S every single time, then it might be too inefficient for us, right? So one idea that we might have is to construct a matrix, so a V by V matrix that tells us whether there is a path from S to T, right? So similar to an adjacency matrix where that tells us if there is an edge from S to T, but instead of that, we want a matrix that tells us if there is a path from S to T, right, for each pair of vertices, ST. All right, so this matrix is called the transitive closure matrix or reachability matrix, and we'll abbreviate it as TC, right? And it's a 2D matrix, right, 2D array, and TC, ST will be true if there is a path from S to T, right? And it'll be false otherwise. All right, so here is an example graph, right? And on the left, I have the adjacency matrix of the graph. All right, so for example, let's look at vertex 6. Right, so vertex 6 has edges to 1 and 2. So 6, 1, and 6, 2 will have a 1. And, whoops, and 0, 4, and 5 have edges to 6, right? So if we look at column 6, row 0, row 4, and row 5 will have 1s, right? Because these vertices have edges to 6. Okay, now here's the reachability matrix. Right, so remember the reachability matrix tells us if there's a path from S to T. Right, so for example, let's look at 5 to 1. So is there a path from 5 to 1? Yes, there is, because we can go 5, 6, 1. Right. So if I look at the reachability matrix, right, row 5, column 1, there's going to be a 1, right, because we can go from 5 to 1. All right, and in this case, we say that vertices can't reach themselves unless there is an actual self loop at that vertex, or unless there is like a cycle involving that vertex, right? So in this case, we say that 5 doesn't have a path to itself, right? So this cell here, 5, 5, will contain a 0, but since 2 contains a self loop, we'll say that we'll put a 1 here, right? Because 2 can reach itself via the self loop. All right, so what we want to do is we want a method to compute this matrix, right? This reachability matrix. Okay, so one way to compute it is to perform a BFS or DFS from every vertex, right? That's obvious, right? So we perform a DFS from 0. That tells us what vertices we can reach from 0. Then we perform a BFS from 1. That tells us what vertices we can visit from 1, and so on. Right. But another way we can do it is to use an algorithm called Warshall's algorithm. Right. And this algorithm doesn't require a graph traversal. And I'll show you how it works here. Right, so the idea behind Warshall's algorithm is that there is a path, so for 2 vertices, S and T, there is a path from S to T if there is an edge from S to T, or there is a path from S to T via 0. Right, so in this case, we can see that there is a path from 1 to 2, right, because there is a path from 1 to 2 via 0, right? Or there's a path from S to T via vertices 0 and 1. Right, so on the left, this is the original graph, right? And this is the adjacency matrix for that graph, right? So over here, this extra edge here is showing us that there's a path from 1 to 2 because there's a path via 0, right? In the next diagram, we can see that there's a path from 3 to 0 because there's a path via vertex 1, right? So, the path is, you go from 3 to 1 to 0, so that tells us that there's a path from 3 to 0. So this edge here is just showing that, this bolded edge. There is also a path from 3 to 2, right? Because we can go from 3, 1, 0, 2. Right? So 3, 1, 0, 2. And there's also a path from 3 to itself, right? Because we can go from 3 to 1 back to 3, right? All right. Or, so, there's a path from S to T if there's an edge from S to T, or there's a path from S to T via 0, or there's a path from S to T via 0 and or 1, or there's a path from S to T via 0, 1 and or 2, or so on, right? So the goal of Warshall's algorithm is to start, from just the edges and then determine reachability using these edges, right? From the ground up, so to speak. All right, so the algorithm goes through a number of iterations, right? So in the first iteration, it finds all the pairs of vertices, ST, where there is a path from S to T via 0, right? Then in the next iteration, it checks vertex 1 and finds all the paths where there's a path from S to T via 0 or 1, right? And it keeps adding on vertices until we've gone through all the vertices. Right? There's an example in a second, so don't worry if that sounds confusing. All right, so during a particular iteration, so on the kth iteration, the algorithm, on the kth iteration, the algorithm tries to determine if there is a path between S and T using just the vertices from 0 to k as intermediate vertices. All right, so what this diagram is showing is that on the kth iteration, right, if we know that there is a path from S to K, right, and we know that there is a path from K to T, using only vertices from 0 to K minus 1, then that means we have a path from S to T using vertices from 0 to K, right? Because we just go from S, we follow the path from S to K, then we follow the path from K to T. And this tells us that there is a path from S to T. All right, so the corresponding code for that is here, right? So if there is a path from S to K, right? So TC SK, and there is a path from K to T, so TC KT, then that means there is a path from S to T, right? So we set TC ST to true. All right, so here's the pseudocode for the algorithm. Right, so our input is an adjacency matrix. Right, so the adjacency matrix of some graph. And what we do is we create our matrix. Right, so we're creating a new matrix here, our reachability matrix. So we initialize that to false. Right, and the first thing we do is we get all the edges from the original graph, and we store it in our matrix. Right, so for each vertex S and for each vertex T, if there is an edge from S to T, then we store it in our TC matrix. Right? And now what we do is we loop through all our vertices. Right, so we have 3 nested loops here. So for each vertex k in the graph, so from 0 to n minus 1, we check every pair of vertices S and T, right? So for each vertex S and for each vertex T, if there is a path from S to K and there is a path from K to T, then that means there is a path from S to T. Right? So this is the if statement that I showed earlier. Right, so if there is a path from S to K and a path from K to T, then there is a path from S to T. All right, and here is an example with a relatively small graph. All right, so what we want to do is find the transitive closure of this graph. Okay, so first we're going to initialize this reachability matrix with the edges from the original graph. Right, so we see that there's an edge from 0 to 2. So this there's a 1 in this cell. There's an edge from 1 to 0 and 1 to 3. So there are 1s in these 2 cells. And there is an edge from 3 to 1. So there's a 1 in this cell. Okay. So now we're going to go through our iterations. Right, so in the first iteration, k is equal to 0, right? And what this means is we're going to use 0 as an intermediate vertex. Right? So we're going to find all the incoming edges to 0 and all the outgoing edges from 0, right? And if there's a path from if there's an edge from S to 0 and there's an edge from 0 to T, then that means there's a path from S to T. Right? So during the first iteration, we're going to notice that there is a path from 1 to 0 and a path from 0 to 2. All right? So, and that's because we'll be able to figure that out by checking these cells of the matrix. Right? So there's a path from 0 to 2, and there's a path from 1 to 0, and there's a path from 0 to 2. All right? So what this tells us is that there is a path from 1 to 2, right? So we put a 1 in this cell, all right? Right, and that's it for the first iteration, right? Because there are no more, incoming or outgoing edges from 0. All right, in the second iteration, we're going to focus on vertex 1, right? And we're going to look at all the incoming and outgoing edges for 1. Right, so first of all, we notice that there is a path from 3 to 1, and there is a path from 1 to 0, right? Shown over here. Right, so there's a path from 3 to 1 and a path from 1 to 0. So this tells us that there is a path from 3 to 0. Right? So we set this cell of the matrix to 1. All right, what else do we know? Well, we also notice that there is a path from 3 to 1 and a path from 1 to 2. Right? So that tells us that there's a path from 3 to 2. Okay? So we set this cell over here to 1. There's also one more thing that we notice. So there's a path from 3 to 1, and then path from 1 to 3. All right? So that tells us that there is a path from 3 to itself, right? So we set this cell of the matrix to 1. All right, so that's the second iteration. Right, so we're continually adding edges, right, to our graph to indicate whether there is a path between two vertices. Right? So in the next iteration, k is 2, right? And we see that there are actually no pairs of vertices such that the first vertex has a path to 2 and 2 has a path to the second vertex. All right, so and that's because 2 doesn't have any outgoing edges, right? So what do? Well, that means we just don't update the matrix, right? So there's nothing to update. Okay, so in the next iteration, so this is the final iteration, k is equal to 3. Right, so what do we notice? Well, we notice that there is a path from 1 to 3, right? And we also see that there's a path from 3 to 1. Okay, so what does that tell us? That tells us that there is a path from 1 to itself, right? So we put a 1 in this cell. And now we're done. Okay? So, after the algorithm is finished, what we notice here are, so these solid lines are the original edges of the graph, right? And these dotted edges are the paths that we've deduced, right? So we've deduced that there's a path from 1 to 2, from 1 to itself. We've deduced that there's a path from 3 to 0, from 3 to 2, and from 3 to itself. Okay? So that's Warshaw's algorithm. So how efficient is it? Well, in the pseudocode, we can see that we have 3 nested loops here, right? Each of them going through all the vertices in the graph. Right? So that means our algorithm is O of v cubed. Right? What is the space complexity? Well, the algorithm needs to create a v by v matrix, right? The reachability matrix. So its space complexity will be O of v squared. Right, so if your graph is really large, right? For example, if it has hundreds of thousands of vertices, then running this algorithm could be a problem because you need v squared space. All right, and what is the benefit, right? So the time complexity is O of v cubed. That's pretty inefficient, right? So what's the benefit? Well, now that we have the reachability matrix, checking reachability between vertices is now O1, right? And this makes up for the slow setup, which is O of v cubed, if we frequently need to perform the reachability check. Okay. All right, so that is Warshaw's algorithm, and that's all of the digraph algorithms that I wanted to talk about. So in the second half, we'll talk about Dijkstra's algorithm, which is an algorithm on weighted graphs. All right, so let's take a break. We'll come back at 3:05. Okay, so let's continue on. Okay, so we've just looked at some algorithms on directed graphs. So now let's switch over to weighted graphs and see what algorithms we have. Okay, so the first algorithm that we're going to look at is Dijkstra's algorithm, which is an algorithm for finding the shortest path in a weighted graph, right? And on Wednesday, we'll look at a few other algorithms, but in this lecture, we'll just focus on Dijkstra's algorithm. All right, so first of all, Dijkstra's algorithm is used to solve the shortest path problem in a weighted graph. Right, so in a weighted graph, so remember that a path is just a sequence of edges, right, connected end to end. Right, so here's an example path, right, so V0 to V1 to V2 and so on, and each edge is weighted, right? And the cost of a path is the sum of edge weights along the path, right? So the cost of this path would be the first weight plus, or the weight between V0 and V1, plus the weight between V1 and V2, and so on, right? And what is the shortest path? Well, the shortest path between two vertices is just the path between them with the minimum cost, right? So that's just some terminology. So what are some, so there are a few different shortest paths problems. So for example, there is the source target shortest path problem. So in some cases, you'll be given a starting vertex and an ending vertex, and you just want to check if there is a path between them, right? Or you just want to find the shortest path between them, sorry. There is also the single source shortest path problem. So that's where you're given a single vertex, which is your source vertex, and you want to find the shortest path to all other vertices in the graph, okay? Then we also have the all pairs shortest path problem, which is where we want to find the shortest path between all possible pairs of vertices. All right, so different problems. And Dijkstra's algorithm is mainly used for the first two, right? So we use it to find the shortest path between two specific vertices, or we use it to find the shortest path from one vertex to all other vertices, right? And we'll mainly focus on the single source shortest path, so finding the shortest path between one vertex and all the other vertices. Right, so firstly, why do we even need Dijkstra's algorithm? Right, so in week 5, we saw that BFS finds us the shortest path, right, in an unweighted graph. Right, the problem is, in a weighted graph, the shortest path between two vertices isn't necessarily the path with the least number of edges, right? So in this example graph, right, the shortest path from 0 to 1 is not just this single edge from 0 to 1, right, which costs 5, but actually this path here from 0 to 2 to 1, right, and that costs 4, right? All right, and the path from 0 to 3, the shortest path from 0 to 3, is not this path 0 to 3, which costs 4, but this path 0, 4, 5, 3, which costs 3, okay? So, yeah, so that means we can't use BFS in order to find the shortest path in a weighted graph, right? We have to use another algorithm, like Dijkstra's algorithm. All right, so Dijkstra's algorithm, so what is it? It's used to find the shortest path in a weighted graph with non-negative weights. All right, so negative weights can cause problems for Dijkstra's algorithm, so we assume that the graph doesn't have negative weights. All right, so what are the data structures used in Dijkstra's algorithm? We saw that in BFS, we use a visited array and a queue, right? In DFS, we use a visited array and a stack if we're doing DFS iteratively, or we used recursion, right? In Dijkstra's algorithm, we use a distance array, right? So the purpose of the distance array is to keep track of the shortest currently known distance to each vertex. Okay, so that's the distance array. We also have a predecessor array, right? So the predecessor array has the same purpose as in BFS and DFS. Whoops. Right, so the purpose is to keep track of the predecessor of each vertex on the shortest currently known path to that vertex. Right, and after Dijkstra's algorithm has finished, we can use it to construct the shortest path to each vertex. All right, we also have a set of vertices, right, and the point of this set of vertices is to store unexplored vertices. Right, so every time we explore a vertex, we'll remove it from this set, and when we're deciding which vertex to visit next, we choose a vertex from this set. All right, and this is deliberately abstract because there are different ways you can implement a set of vertices, and we'll talk about that later. All right, so at a high level, here is what the algorithm does. All right, so first we create and initialize our data structures. All right, so we initialize, so first of all, we have our distance array. Right, so what do we initialize that to? Well, at the start of the algorithm, we don't know whether there is a path to any other vertices, right? We don't know what the distance is. So what we do is we just initialize it to infinity, right? So initialize all the distances to infinity. And since C doesn't really have an infinity, and other programming languages also don't really have infinity, we can use a large integer, like int max. Okay, and the assumption there is that there is no path there is no path that actually costs more than int max, right? So that's the assumption we're making when we use this. All right, our predecessor array, so we initialize that to -1, just like in BFS or DFS. And we initialize our set of vertices to contain all the vertices. Okay. All right. What we do next is, since we know what vertex we're starting at, we're going to set its distance to 0. Okay. That's because the distance from the starting vertex to itself is 0. Okay, and so that's the initialization phase of the algorithm, right? So what happens next is we have just a loop that continues while the set of vertices is not empty. Right, so what we do is we remove the vertex from the vertex set with the smallest distance. Right, so we remove the vertex from the vertex set that is closest to the starting vertex, and then we explore that vertex. Right, so what does it mean to explore? Well, we look at all of the edges from V. Right, so for each edge VW, we check if using this edge gives us a shorter path to W than the path that we have currently stored in our arrays. Right, and if we find a shorter path to W, then we update W's distance and predecessor. Right, and this is called edge relaxation, and we'll have a closer look at edge relaxation now. All right, so edge relaxation is a really common operation in the algorithm. So in what context do we use it? Right, so during Dijkstra's algorithm, right, the distance of predecessor arrays, they don't necessarily contain the full information about the shortest path, right? So they only contain information about the shortest path discovered so far, right? So we need to update them if we find a shorter path to a vertex, right? And we do this via edge relaxation. All right, so how do we perform edge relaxation? Right, so we perform it when we're considering edges, right? So suppose we're considering this edge here from V to W with a given weight, right? So at this point in the algorithm, we have the following information, right? So first of all, we know the length of the shortest known path from source to V, right? And this is stored in dist V. And we also know the length of the shortest known path from source to W, right? Which is stored in dist W. Right, so we know the shortest, the length of the shortest path from S to V and from S to W, right? When we perform edge relaxation, we take the shortest path from S to V, so the shortest path found so far, and we extend it using the edge that we're currently considering, right? So we extend it using the edge from V to W, and this creates a new path from S to W, right? So as you can see here, this is the path from S to V. We're adding on this extra edge, and that creates a new path from S to W. Okay, so now we have two paths from S to W, right? So we have the shortest known path, which is from S to W, and the distance is stored in the distance array, right? And we have this new path where the distance is the shortest distance from source to V plus weight, right? So two paths, one has a cost of dist W, and the other path has cost dist V plus weight, okay? So what we want to do is check if this new path that we've found is shorter than the currently known path, right? So if dist V plus weight is less than dist W, right, so if the length of the new path is shorter than the length of the currently shortest known path, then we update our distance. So we update the distance to W to dist V plus weight, right, because we found a shorter path. And we update the predecessor of W to V, okay? Because now we found a shorter path from S to W, and the predecessor of W on this path is V. Okay, so here's a more concrete example of edge relaxation. So suppose we're performing Dijkstra's algorithm on this graph, starting at S, and currently, so this is at some point during the algorithm, we have this information, right? So we know that the shortest distance to V so far is 8. We know that the shortest distance to W so far is 12. And we know that we have an edge from V to W of weight 3. All right, so now we want to perform edge relaxation on this edge from V to W. Right, so if we take this path from S to V, right, and we extend it using this edge, that gives us a new path from S to W, right? And the length of this path is 11, right? 8 plus 3. All right, and since this path is shorter than the shortest known path to W, which is 12, we update our distance to W to 11, right? And we also update the predecessor of W to V, right? So before we performed edge relaxation, this was the shortest path to W, right? And the predecessor of W was I, right? After we perform edge relaxation, this is now the shortest path from S to W, and the predecessor of W is V. All right, so here's the pseudocode for Dijkstra's algorithm, right? And this is the single source version of the algorithm. So you might have another version that takes in both a source and a destination. Okay, so what do? Well, we create our distance array, initialized to infinity. We create our predecessor array, initialized to -1. We create a vertex set containing all the vertices of the graph. And then we set the distance of the starting vertex to 0. Right, and then while the vertex set is not empty, we find the vertex in the V set such that the distance is minimal. So we find the vertex in the V set with the smallest distance. We remove it from the V set. Then for each edge from V, we relax along that edge. Right? And relaxation is just what I showed here. Okay. All right, so here's an example. Right, so we want to perform Dijkstra's algorithm starting at 0. Right, so let me hop over to the example. Okay, here we go. All right, so here's the initial state of our algorithm. Right, so all the distances are infinity except for our starting vertex, which is 0, and all the predecessors are -1. All right, and here's the main loop of the algorithm on the right. Here's the graph. All right, so the first step in the loop is to remove the vertex from the V set with the smallest distance. Right, so at the beginning, this will be our starting vertex, right, 0, right, because the smallest, or the vertex with the smallest distance is 0. Right, so remove 0. What do we do now? Well, we explore all the edges of 0. Right, so there's an edge from 0 to 1, from 0 to 2, from 0 to 3. Right, so let's look at the first edge. Right, so we want to relax along this edge from 0 to 1. Right, now, so the question is, if we use this edge, right, what is going to be the cost of the new path to 1, from 0 to 1, right? Well, the cost is going to be the distance to 0, which is 0, plus 14, right, plus the weight of the edge, right? So the cost of this new path is going to be 14, right? And since 14 is smaller than the currently known distance to 1, which is infinity, we update our array, right? So we update the distance to 14, and we update the predecessor of 1 to 0, okay? All right, so that's the first edge. Now let's relax along this edge from 0 to 2. Okay, so the cost of, so if we use this edge, the cost from 0 to 2 is going to be 0 plus 9, right, which is 9. Right, and since 9 is smaller than infinity, we update the distance to 2 to 9, and we update its predecessor to 0. Right, and we do the same thing for 3. Right, so the cost of the new path will be 7, so we update the distance to 7, and we update the predecessor to 0. All right. So this is the first iteration of the algorithm. Right, so now we're done with exploring 0. So 0 is no longer in our V set. Right, so I've graded out here. All right, so let's remove another vertex. Right, so what do we remove? Well, out of the remaining vertices, the one with the smallest distance is 3. Okay, so we're going to remove that. Right, and now we're going to explore all the edges from 3. Right, well, we have an edge from 3 to 0, but actually there's no need for us to consider this edge, right? And that's because 0 has already been explored. All right, so once we finished exploring a vertex, there's no need to consider any edges to it again, right? So we can sort of ignore this. All right, so let's look at the next edge from 3 to 2. So if we use this edge, right, to get to 2, the cost of this path is going to be the shortest distance to 3, which is 7, plus the weight of this edge, which is 10. Right? So 7 plus 10 is 17. And 17 is the cost of this new path, right? But we already have a path from 0 to 2 that costs 9, right? So since this is not a shorter path, we don't update our arrays, okay? Yeah, so we don't update our arrays. Right, so the next edge is from 3 to 5. Right, so if we relax along this edge, then the cost from 0 to 5 is going to be 7 from the array, right, plus 15, which is 22. Okay, so since 22 is smaller than infinity, we replace the distance with 22, and we also replace the predecessor with 3. Okay. All right, and now we're done with exploring 3. All right, so the next vertex is 2. Right, so out of the remaining vertices, 1, 2, 4, and 5, the vertex with the smallest distance is 2. So we'll remove 2. And now we explore all of the edges from 2. Right. Okay, so first, we don't need to consider this edge from 2 to 0, because 0 has already been explored. Right, but how about this edge? Right, so if we relax along 2, 1, right, then what is the distance going to be from 0 to 1? Right, well, it's going to be 9 from the distance, right? So remember, 9 is the shortest distance from 0 to 2, right? So we take 9, and we add on the weight of this edge, which is 4, and that gives us 13, right? So 13, now the current shortest distance to 1 is 14, right? Which is what we've stored in our distance array. Right, so since 13 is smaller than 14, we update the distance to 13, and we also update the predecessor to 2, okay? All right, so the next neighbor is 3, but since we've already explored 3, we don't need to consider this edge. Right, the next neighbor is 5. Okay, and now we want to relax along this edge, right? So if we relax along this edge, the distance to 5 is going to be 9 from the distance array plus 3, right? So that's going to be 12. And since 12 is smaller than 22, right, we update our distance array to 12, and we also update the predecessor to 2. Okay, so now we're done with exploring 2. All right, so which vertex do we remove from the V set next? Well, we have 3 vertices, right? 1, 4, and 5. Right, the vertex with the smallest distance is 5, right? So we remove 5. All right, so let's explore 5, right? Well, 2 has already been visited, so we can ignore 2. 3 has already been visited, so we can ignore 3, right? But we haven't visited 4 yet. Right? We haven't explored 4 yet. So let's relax along this edge. Right, so what will be the cost of this new path to 4? Right, well, it's going to be the cost, well, it's going to be the shortest, length of the shortest path from 0 to 5, which is 12, plus the weight of the edge from 5 to 4, right, which is 8. So 12 plus 8 is 20. And since 20 is smaller than infinity, we update the distance to 20, and we update the predecessor to 5. All right, and now we're done with exploring 5. All right, next. So we have only 1 and 4 left. So since 1 has the small distance, we remove 1. And now we explore its edges. Right, so 1 has an edge to 0, but since 0 has already been explored, we skip it, and same for 2. And now 1 has an edge to 4 of weight 5. Right, so if we use this edge to get to 4, right, the cost of the path will be 13. Right, so 13 is the shortest distance to 1, plus 5, right, which is the weight from 1 to 4. So 13 plus 5 is 18, right? And since 18 is more than 20, which is the current shortest distance to 4, we update the distance to 18, and we update the predecessor to 1. All right, now we're done with exploring 1. Right, so now we remove 4 from the V set, right? And since both of 4's neighbors have been explored already, we can skip both of them, and we're done. All right, and now we're finished. Okay, so that's the example. So here I have the state of the arrays at the end of each iteration. So this is after the first iteration, this is after the second, and so on. Right, and this is the result at the end. Right, and here I've highlighted the shortest paths from 0 to every other vertex. Right, so the shortest path from 0 to 1, for example, is 0 to 1. The shortest path from 0 to 5 is 0 to 5. The shortest path from 0 to 4 is 0 to 1, 4, and so on. Right. All right, so what do we have now? Well, now we know what the shortest distance from 0 to every other vertex is. And we also know, we can also use the predecessor array to reconstruct the shortest path to each vertex. All right, so to reconstruct the shortest path, we can do the same thing like we did for BFS, right? So we just trace backwards through the predecessor array. All right, so to get the shortest path from 0 to 4, for example, well, we start at 4, right? We see what its predecessor is. So 4's predecessor is 1, so now we trace backwards to 1. Now we see what 1's predecessor is, which is 2. So we trace backwards to 2. Then we see what 2's predecessor is, which is 0. So we back trace to 0, and 0 is our starting vertex. Right? So we are done. Right? And this is our shortest path. All right, so now what if we want to find the shortest path between 2 other vertices, right? Where neither of them is the vertex that we started at. Right, so suppose we perform Dijkstra's algorithm starting from 0, and now we want to know the shortest path from 2 to 5, for example. Right? Well, in general, you'll need to rerun Dijkstra's algorithm starting from 2 or 5. Right? So Dijkstra's algorithm starting from a particular vertex, in general, only gives you the shortest paths from 0 to all the other vertices, right? So not the shortest distance between 2 other vertices, right? But there are a few things that you can deduce. So for example, since this is the shortest path from 0 to 4, right? Then we know that 2, 1, 4, for example, has to be the shortest path from 2 to 4, right? Because if there was a shorter path from 2 to 4, then that means there would also be a shorter path from 0 to 4, right? So there are some shortest paths and distances that you can deduce. But in general, if you want to find the shortest path between 2 other vertices, you have to rerun Dijkstra's algorithm. Okay, so now on to a problem which we introduced earlier, right? So the vertex set, right? How do we implement this? Well, we have a few different methods for doing so. Right, so one method is to just use a visited array, right? So similar to the visited array from BFS or DFS. Another way we can do it is to use an explicit array or linked list of vertices, right? So we store all of the vertices in a linked list, for example, and then every iteration we pick one to remove, we remove it, and so on. Right. And the third one is to use an ADT called a priority queue. Okay. So we'll talk a bit about each of these. So in the visited array implementation, all you do is you create a visited array of v booleans, right, initialized to false, and every time you visit or explore a vertex, you just set it to, you just mark it as visited, right? So you're sort of just using this array to tick off all the vertices as you explore them. Okay. So what is the cost of this implementation, right? Well, at the start of each iteration, remember, we have to find the vertex with the smallest distance, right? So that means we have to loop through the array to see which vertices haven't been explored yet and to find which one has the minimal distance, right? So since we have to scan through the entire array, this will be O of v, right? Every time we have to pick a vertex to visit next. All right, so how about the array or list of vertices, right? So if we implement the vertices using an explicit array or list of vertices, then we just store all the vertices in an array or linked list, and after we explore the vertex, we just remove it from the array or linked list, right? So what is the cost of this? Well, at the start of each iteration, we just need to, loop through the array or linked list to find the vertex with the smallest distance. All right, and the cost of this is O of v, right? Because we just have to loop through the array or list. All right, so the last option is to use a priority queue. Right? So a priority queue is an ADT where each item has a priority and it has two main operations. Right? So first, it has an insert operation. So the insert operation inserts an item with a given priority. Right? And the other operation is delete, where you delete the item with the highest priority. All right, so how would we actually use the priority queue? Well, what we do is we use it to store the vertices, and along with each vertex, we use the distance to that vertex as its priority, right? So, for example, at the very beginning of the algorithm, let me just jump over here. Right, what we would do is we would store all of these vertices into the priority queue, but 0, we would give a priority of 0, right? And that means it has the highest priority. And for the other vertices, we would give them a priority of infinity, right? Okay, and yeah, so at the start of each iteration, we just use the delete operation to remove the vertex with the highest priority. And then, yeah, and that's it. Right, and a good priority queue implementation will have O log n insertion and deletion. All right, so this is by far the best implementation for a vertex set, for a V set, right? And we'll discuss priority queues in more detail next week, right? So you don't have to know how to use a priority queue right now. If you were to implement Dijkstra's algorithm right now, you would be perfectly fine using a visited array or using a list of vertices. All right. All right, so now, right, so Dijkstra's algorithm is one of the first non-trivial algorithms that we've covered, right? So the algorithms that we covered previously, like sorting algorithms, it was easy to see that they are correct, right? That they correctly sort items just by the way they work, right? Right, but with Dijkstra's algorithm, it's not so obvious that it does work. So let's try and show that it does. All right, so how do we prove that the algorithm works? With most algorithms, we prove them using induction. All right, so put your mathematics hat on. Hopefully you remember how induction works. Right, with induction we have base case, and then we have an inductive case where we assume that some property is true. So let's see how it works for Dijkstra's algorithm. All right, so the main aim of the proof is to show that before and after each iteration, we want to prove two things, right? So the first thing is that for all the nodes that we've explored so far, right, the distance array contains the shortest distance to that vertex, right? So this S is the shortest distance from source to S. All right, the second thing we want to show is that for all the unexplored vertices, right, the distance array contains the shortest distance to that vertex via explored nodes only, okay? So it might not contain the absolute shortest distance, but it does contain the shortest distance via explored nodes. All right, and if we are able to prove these two things, then at the end of the algorithm, all nodes are explored, right? So that means by this first thing that we prove, right, that means the distance array is going to contain the shortest distance from the source to every other vertex. All right. All right. So now so in induction we first have to prove the base case. Right. So the base case is the start of the first iteration. Right. So at the start of the first iteration, well, we know that this first property holds, right? Because we haven't explored any vertices yet. All right. And we also know that the second property holds. That's because there are no explored vertices, right? So, for the starting vertex, distance to that is obviously going to be 0, right? But for all other vertices, the distance is going to be infinity, okay? All right, so that's the base case, right? So now let's apply the induction step, right? So at the beginning of the induction, right, we assume that these two properties hold at the start of an iteration, and what we want to show is that at the end of the iteration, the property still holds, right? So that means, at the beginning of each iteration and at the end, the property holds, which means the property holds all the way through the algorithm, and at the end, we've proven what we wanted to. Okay. Yeah, so assume that these two properties hold at the start, and here I just have an example graph. So assume that these green vertices have been explored already, and these red vertices haven't been explored yet. Okay. So now, remember at the start of the iteration, we're trying to choose the next vertex to explore, right? So we need to choose the vertex with the minimum distance, right? So let S be an unexplored node with minimum distance. Okay, so let S, so suppose this is S, right? So this is the unexplored node with the minimum distance. And what we're going to claim is that this distance to S in the distance array is the shortest distance from source to S. Right? So we're going to claim that dist S contains the shortest distance from source to S overall. All right, and why is this so? Well, let's consider, when, is it possible that it's not the shortest distance? Well, if there is a shorter path to S via explored nodes only, so for example, this path over here, right, so this dotted path over here, then we would have updated distance with the distance array with that distance while exploring this vertex, right? So if this path is shorter than this path over here, then we would have updated the distance when we were exploring this node over here, right? Okay, so that's not possible. Now, is it possible that there is a shorter path to S via an unexplored node? Right, well, here's an example. So if this path over here, right, via an unexplored node is shorter than our shortest path over here, right, then what this means is that the distance to this node over here, right, must be shorter than the distance to S, right? Since this path over here goes via this vertex, right? And that means, and this is a contradiction, right? Because we assumed earlier that S has the minimum distance, right, out of all of the unexplored nodes, right? So this situation over here is impossible, right? So that means that, if S is the unexplored node with minimum distance, then that means distance array contains the shortest path to that vertex overall, right, in the entire graph. All right, so now we know that dist S is the shortest distance from source to S. All right, so what happens after we explore S? Right, so after we explore S, we know that this first property still holds for S, right? Remember, let's remind ourselves what the first property is, right? So the first property is for all explored nodes, right, the distance array contains the shortest distance to that vertex, right? Well, since we showed that, before exploring the node, the distance array already contains the shortest distance to S, right? After we explore S, the distance isn't going to change, right? So yeah, the distance array, so we're not going to update the distance to S while exploring S. Right? And the same is true for all the other explored nodes, right? So these are the green vertices. Right, and we also know that after exploring S, 2 still holds for all the unexplored nodes. Right, so what was 2? So 2 is the property that for all unexplored nodes T, right, the distance array contains the shortest distance to T via explored nodes only, right? So why does 2 still hold? Well, suppose here that before exploring S, right, this is the shortest path from source to this node over here, right? So if there is a shorter path to this vertex via S, right? So if this path over here happens to be a shorter path than this solid path over here, then that means we would update the distance to this vertex while exploring S, right? So while exploring S, we would have found a shorter path and we would have updated the distance, right? Otherwise, if this path is longer than the path that we've currently stored, then that means we wouldn't update the distance, right? And it would just remain as what it was. Okay, so that's the proof of why Dijkstra's algorithm finds the shortest path. All right, so now for analyzing Dijkstra's algorithm. Right, so what does Dijkstra's algorithm do? Well, it considers each edge once, right? Because for every vertex in the graph, it considers all the edges from that vertex. So in total, that's E edges. Right? And if your graph is undirected, then it'll consider each edge once in each direction, right? But that's just 2 times E, which is just O of E. Right, so this part contributes O of E, okay? So what else does the algorithm do? Well, the algorithm has V iterations, right? So the outer loop has V iterations, and every iteration, we have to find the vertex in the V set with the minimum distance, okay? And the time complexity of this depends on how you implement the V set, right? So we looked at a bunch of implementations for V set earlier, right? So if you use a Boolean array, then it's going to cost O of V per iteration, right? So the overall cost is going to be O of E plus V squared, because you've got V iterations, and that will simplify to O of V squared, right? Because V squared is definitely going to be greater than or equal to E. All right, if you use the array or list of vertices to implement the V set, right, then that means, then we saw earlier that the cost of this is O of V per iteration, right? So the overall cost is the same as for the Boolean array, right? So it's just O of V squared. All right, now if you use a priority queue to implement the V set, then it's going to cost O of log V per iteration, right? So we said earlier that insert and delete for a priority queue is O of log E for a good implementation. And that means the overall cost is O of E plus V log V, right? Because it's log V per iteration. All right, so if you use a priority queue, then this is a better time complexity than if you use a Boolean array or a list of vertices. All right, so that's the analysis, right? So the best you can do with Dijkstra's algorithm is E plus V log V. All right, so here are some other shortest path algorithms for your curiosity. That we're not going to cover, by the way. So Floyd-Warshall algorithm is another well-known algorithm, and it's good at computing all pairs shortest path, right? So all pairs shortest path means find the shortest path between all pairs of vertices. All right, and unlike Dijkstra's algorithm, it works for graphs with negative weights. Okay, another algorithm is Bellman-Ford. So this algorithm does work for negative weights, and it also detects negative cycles, right? So if your graph has a negative cycle, then there might not be a shortest path, right? Because what you can do is you can go around the cycle and just keep accumulating negative weights, right? And then your shortest path would just be infinity, or negative infinity, right? So Bellman-Ford has a way to detect that, right? And yeah, these are 2 well-known shortest path algorithms. And I think that's it for the lecture. So yeah, so that's it. I'll see you all on Wednesday, and on Wednesday we'll also talk about assignment 2. Yeah, see you then.